Welcome to lecture 4. Today we will explore one of the most important concepts in material science, the difference between direct and indirect bandgap semiconductors. This concept is not only theoretical, it directly determines whether a material can be used to build lasers, light emitting diodes, that is LEDs, or solar cells. Let us begin with the energy versus momentum diagram, commonly called EK diagram. In this diagram, the vertical axis represents energy and the horizontal axis represents momentum. The quantity K, that is momentum, denotes the crystal momentum of an electron moving inside a periodic lattice. The physical momentum P is related to the crystal momentum by P is equal to h cut K. First, consider a direct bandgap semiconductor. Here, the maximum of the valence band and the minimum of the conduction band occur at the same value of K. When a photon interacts with an electron, it supplies sufficient energy to cross the bandgap. However, photons carry almost negligible momentum. Because both bands align at the same momentum value, the transition appears vertical on the EK diagram. No momentum change is required. Therefore, no phonon involvement is necessary. This makes the transition highly probable. As a result, we observe high absorption efficiency and a very sharp absorption edge. The reverse process, that is emission, is also highly efficient. Therefore, direct bandgap materials are excellent light emitters. They are widely used in LEDs and semiconductor lasers. Common examples include gallium arsenide, indium phosphide, and cadmium telluride. Now let us contrast these with an indirect bandgap semiconductor. In this case, the valence band maximum and conduction band minimum occur at different K points. An electron cannot simply move upward by absorbing a photon alone. There is no available state at the same momentum. To satisfy momentum conservation, a phonon must participate. The electron must absorb a photon for energy and simultaneously interact with the phonon for momentum. This becomes a three-particle interaction: electron, photon, and phonon. Because of this process is statistically unlikely, absorption efficiency becomes low. Instead of a sharp edge, we observe a gradual absorption edge. Emission efficiency is also weak. Therefore, indirect bandgap semiconductors are rarely used as light emitters. Famous examples include silicon, germanium, and gallium phosphide. To conclude today's lecture, let us connect these quantum ideas to the spectra we observe experimentally. When we record data using spectrometers, we typically observe three main types of spectra. First one is continuous spectrum. This contains all wavelengths within a certain range without interruption. Such spectra are produced by dense hot objects, for example, a tungsten filament or a black body radiator. Second is emission spectrum. Here excited atoms or molecules emit photons only at specific wavelengths. The result is a dark background with a bright discrete lines, each line corresponding to a precise energy transitions. And third type and the main focus of this unit is the absorption spectrum. If continuous light passes through a cooler gas or molecular sample, only specific photons matching allowed energy gaps are absorbed. The observed spectrum appears as a continuous rainbow with dark lines or bands missing. These missing regions indicate where absorption occurred. Today we learn the physics of direct transitions, the role of phonons in indirect transitions, and how quantum processes appear in laboratory spectra. In the next lecture, we will begin studying the instrumentation required to measure absorption spectra accurately. Thank you.